Okay, so my name is Roland Bock. I'm here to talk to you about a library that I wrote over the last few years. It's called SQL++11, and it's an SQL library for C++. And the first thing you should ask when you hear something like this is, why on earth do we need yet another SQL library for C++? I mean, there are so many already. And my answer is pretty much this, a quote from Scott Myers. It's from the second edition of Effective C++, and he says, prefer compile time and link time errors over runtime errors. And to explain why that is applicable here, let's take a look at some code. So this is an example from another SQL library. I think a typical SQL library. This is from CppDB. I didn't choose this for any particular reason. It's just that it was the first that I downloaded and compiled, and it works just fine. And the examples are very cool. So how does this work? Let's see if I can use the pointer here. So we have an insert statement, and we insert into a table some columns, and we have values. We use some parameters for those, and then we just stream in the appropriate values. Okay, not so special. Then turns out that this, then we execute the statement. Turns out that this statement is also a prepared statement, so we can bind values to it again, execute it again. Okay, that's neat. And then later on, we can select values from the table. Again, we're writing a string with some text in it, have a parameter again, stream in a value, and then this time tell the library, okay, we should expect a result row here. And then we, if there are results, then we can access those results either by name lookup, basically that's kind of a map, telling the library what we expect this value to be, and we also can use an index at runtime and say, okay, we expect a double here, and okay, so far so good. And if it's as simple as this, and if we don't have to maintain anything, that's cool. It works. It compiles. We can do that right now. Compiles. Cool. Runs. Wonderful. So not a big deal, right? But as soon as we start maintaining it, or as soon as somebody is not as good in typing, we can introduce bugs pretty simply, right? It's very easy to have a few bugs. And now I've just introduced about 10 bugs in here. Very hard to see, right? I don't know the exact count, but maybe about 10 bugs. But if you store that and compile it, well, it still compiles. No problem with that. Okay, the library is still happy because everything is strings, and when you run it, well, then you run into into errors. So only when you test it, or if you don't have 100% test coverage, when you hit it in production, then you see these errors. And that's pretty hard to debug. So I said when I first saw something like this in about 2008, then okay, that's not the right way to do it. We're in C++, goddammit. We have types. SQL has types. We have expressions. SQL has expressions. There got to be a better way. But it took quite a few years. It required a new standard to do this. In 2008, I wasn't really able to achieve what I wanted. But now with C++11, I have a library, and that's the one that I want to talk to you about. And to give you a feel of how this library works and what it does for you, let's start again with an insert example, and then again with a select example. And I'm going to show you first what a normal insert statement would look like. So in this library, we would always assume that you have some kind of table definition in your code, including also column definitions. And you would use these tables, like you have this tab person and tab feature up there. And then you would use that. Okay, you would have the insert into the feature table now, and then set some columns to some values. Okay. And then you can send that to a database, in this case, just a mockup. But it would work with any other database that you connect to. And that is fine. That compiles. Okay. And I could run it, but again, it's a mock database, so it doesn't do anything. But how about we make a mistake? We spotted the mistake. Okay, so that's very simple. We just misspelled one of the columns. That is something that would never occur to the compiler in a string-based interface, but here it does. Okay, and very easy, clean error message. Okay, you mistyped the name. Cool. Another example would be this. Okay, at least one of these arguments in the set method is not an assignment. Okay, we look at it and see, all right, true. This is not an assignment. Okay, we did something wrong. Just an oversight, of course. But that's what all these errors are that you have in SQL. Most of them are oversights. You just do stupid mistakes. Next one. Okay, invalid assignment operator. Invalid assignment operand. And it tells you that, oh, right. So fatal, that is a Boolean column. I'm trying to assign a string to it. Okay, it looks all right, but if you take a closer look, well, it's a string. Come on. Compiler knows that. Then, oops. The next thing is, at least one sub-expression requires tables which are otherwise unknown. And yeah, if we take a closer look, we realize, okay, we try to insert feature columns, so columns of the feature table, into the person table. I mean, again, that is something that happens with copy-paste. Very, very easy to do that. But the compiler will tell you. And then there are things that I think, as far as I know, I'm not an SQL guru, are not part of SQL, but you can add additional constraints. Like you could say, I don't want certain columns to be set in an insert. Like if I have an auto increment column, then it's not very useful to set this, right? And in 99.99 something % of the cases, you don't want this. And if somebody does it, it's a mistake. So we can define the column in such a way that we say, okay, don't set it in an insert. Or don't set it in an update. We can do this individually. And the compiler will tell us if we try. Right? And goes also the other way around. We can also say that certain columns are required to be set. Right? We say, okay, there is no reasonable default value. Just set it. Okay. By the way, you can also see that, well, this compiles a little bit slower than strings, obviously, because it does a lot more compilation. But it's not too bad, right? And it does a lot of calculation. So as you have seen, this making sure that everything is from the same table and so on. And you will see this, that this is going to be the same with selects, where you can have really huge statements. It does all these calculations at compile time, and it's not so bad. So you can still wait for it, and we can still use it in such a talk. It's not horribly painful to wait for it. Just for completeness, since I'm talking about insert, you can have set everything to a default value. That is here. You can have a multi-column, a multi-row insert, sorry. That is possible, and you can also have a prepared statement. So prepared statement as in the example before, but this time there is no problem with mixing or messing up these parameters of a prepared statement. So what you see here is I say, okay, I want to set the column name to some parameter, and I give it a name, right? And the column feature, I want to set that to something, and I give it also a name. And then I don't have to address the parameters of a prepared statement with some index or some map lookup, or in the example that we've seen before, just by passing in the values in the correct order, which you can mess up so easily. No, you just use members of this parameter struct and say, okay, name should be like Java, and the feature should be 7, and that's it. They know the correct type, they have the correct name. It's very hard to mix up. Okay, questions so far? I'm sorry?
Like a p.name equals parameter f.name.
Which one? This one?
Yeah.
So this is the equivalent of the question mark in the earlier example. So you're just saying, okay, I'm having a parameter here. I'm not setting the value exactly here. I'm saying this is a placeholder, and for a prepared statement in SQL, and I want to set this value later and reuse the query typically. Right. So prepared statements are typically for reuse and running this thing more often, because then the database can compile this once, and you can then just set in the values for each and every one time you want to use this.
I assume that you're filling that in with likes Java.
Yeah.
But the f.name, so on the right-hand side it says p.feature. I'm just trying to figure out how you're making it happen.
How the names get in there.
Yeah, well, f.name and p.feature. Should it be p.name or should it be f.feature?
No, that is a good point. So the question was, if these names are of the if these names are correctly used, because they should maybe be used as p name or whatever feature. The thing is that this is basically using an alias, and you can use any name you want. Any name that is prepared in the code somewhere, you can use there. Anything that has a name can be used there to give a parameter a name. And we will see this with selects in a few moments, how this is going to be used in additional ways. Does that answer your question? Not fully, I know, but okay. Any more questions about insert? Okay. Now let's go to select, and I'm going to skip anything about update and delete, because that's kind of similar to these. If you've seen the talk yesterday about beautiful code, I apologize for these if-null things, but they are good for presentation. So this is a select statement. Now, in a select statement, well, we just call select, and in this case, we select all columns of a table, of the person table in this case, from the person table. Okay, nothing special there. We call where, some condition. This could be more complex, of course. We could have more stuff to it. And then this returns a range of result rows. And the result rows are reasonably constructed in such a way that a row now contains the columns, or no, fields which correspond to the columns of what I've selected. And the person table, well, I didn't show the definition, but it contains an ID, a name, and a link into the feature table. So the result rows now contain exactly members that correspond to what you're looking for. So you don't have to do some weird lookup by index. You don't have to do some weird lookup by using a string at runtime. No, you have members in a struct, and you can address them just as normal members because they are normal members. And they have an appropriate type, so you don't have to tell it that, okay, this is an int and that's a string. That is all done for you by the library. The library will calculate that for you. Okay. So what if it gets a little bit more complicated, and I don't select everything? I mean, if I select everything from the table, then the first thing that's still pretty simple because, well, I have a table definition. I have all the columns in there. Okay, then I can derive a row from that very easily. But what if I select only a subset of these tables or many more? Then, okay, does that compile? Oh, still with the insert. What do I do here? And no, it doesn't. So let's go back here. Well, this doesn't compile anymore because, well, we selected only a name, and then, of course, our row should only contain a name. It shouldn't contain anything else because that would be confusing, right? So, yeah, if I try to access an ID here, well, that shouldn't work, and it doesn't, as I've just shown. Same with name clashes. If I select two columns with a column with a name with the same name, then okay, that shouldn't compile, and it doesn't because it's an ambiguous lookup. And what we can do here is pretty much the same as what we can do in SQL. We can assign another name to it. We can say, okay, select this as something else. And I'm just using some name, and now it works. And we have and should be a string. Oops. And now we can select a member with this weird made-up name. Okay, that's magic. So it looks like it, but I was prepared. See some relief over there. So there's only one macro in this library that you might want to use. Only one. And that is this alias provider. It provides you with a class and an object that you can use in just this way, so that you can use it as something that gives you a name, and then you just use it with a name. And you create members of these result rows with the appropriate name, and still the appropriate type, of course. And the macro is simple. If you really insisted, you could write it on your own, or write the code out. I think it's a 5-liner or something like that. So it's not bad. Otherwise, I don't like macros. Anything special in addition here? No, I mean, yeah, the queries get slightly more complex. So we have a join here, but other than that, let's move on. This is just to give you a feeling of what the library can do, and certainly not covering everything. Oh, so this compiles. Yeah, about the name aliasing. I mean, if you say you're doing a self join, right, and you're selecting all columns from the left side and all columns from the right side, and you have a table with, say, 20 columns, then you don't want to assign each and every single one of those a different name. That would be terrible. That would be horrible, unmaintainable as well. For this, we have a feature called multi-column. So you can group columns together into into a group, and then give that group a name. In this case, I selected all columns from the one table and gave this the name of the table. And I selected a few columns from the other table and gave that also, this group, the name of the table. And then the row now also has this hierarchy. So you, first you have to access the group, which is accessed through the name of the table, and then you access the individual field. And there's no name clashes. Good.
I have a column name and first name, but I concat that to full name.
So you mean if you could use a concat function?
Yeah.
Yes. Do I have an example of that? Not handy, but yes, you can select. You can use that. So yeah, you can do anything you want, and typically most of the stuff that you can do in normal SQL there. So you could use a count function, for instance, to count arguments, and you can concat, and you could add stuff to it, or whatever you want. Most of the, in many cases, that would result in something that doesn't have a name naturally, and then you would just assign a name with this as method to it. In the specific case of methods like concat and count, it would already have a name just for convenience. It would be just the name of the function. And then, well, if you have several of those, then you would have to use names again over there.
Does it support subqueries? Like if it did dot from dot select, would that be an additional subquery in SQL query?
Hey, next example. So the question was subqueries. Yes, and that was the last example that I wanted to show in the editor and for the compiler. We have subselects here, several. So first of all, we define a select S, and it has in the where clause, it compares the name to any something. I mean, this is not a reasonable query. I mean, it just made this up to show it off exactly like this. And it has the any contains a subselect. All right. Then we have some more functions, so group by and having. You have the like here. You have order by, limit, offset. So quite a lot, and of course that's not nearly complete. And then we give this subselect a name, right? And we could do this all inline, but it's more ugly. And this X now over there is just this select that we just defined, but with a name. And if it has a name, then we can use it as a table in the next select in the from, right? So that's what we're doing here. So we are selecting from the person table and join this with X on an expression. And again, X has then appropriate numbers with appropriate names and types, right? And we can select from this virtual table. And yeah, that is what you see here. So we've selected the ID from the person table and the name from this virtual table. And the result, again, has the same neat features that members have reasonable names. All right. That is all I wanted to show in the compiler and as editor, and to give you a feeling of what this library can do for you. And I didn't want to bother you with making mistakes in here. I tried to keep the error messages as short as in the examples for the insert. It's not always possible, but yeah, I'm trying to do a good job there. And if you see something which is really ugly, just let me know. All right. Any more questions for select? Good. All right. So this is what I want to go for. Prefer compile time and link time errors to runtime errors, because I really hate runtime errors. Right. So one of the questions was, how does this work? Basically, with the names. Okay. And if anybody has seen my lightning talk, this is not the way that I want it to work, but this is how it does. Okay, so the basic idea is to have templates like these, lots of them. For each column that you have, for each table that you have something like this. Okay. And this is how you basically, or this is the basic idea of how to use it. Okay, you have some struct or a template or whatever, and you inherit from such a template and give it a type. And what it does is it feeds in a member of the appropriate type, the type that you've given, with the appropriate name, the name from this member template. So this struct now has an int member with a name feature. Okay, that is the basic idea, and if you grok that, then you should be able to understand the rest. So this is, as I said, we have column definitions and table definitions in the code. This is what a column definition looks like. So one of these featured columns that we've seen. So I won't go into everything of that, but one of the important things is that it has this name struct, which I can move around easily, and this contains such a member template. You recognize that, and that has a member called feature, some access operators, which are there for more obscure reasons. You're probably not going to use those unless you develop something within the library. And then some traits which say that, well, this is an integer, and this is something that requires an insert, right? Okay. And this is a table that is used in combination with these columns. Well, the table is, the most important part about the table is that it has, inherits from a variable template. First argument is itself, so this is CRTP. And the following arguments are the column definitions that we've just seen. And the rest inside this class is more or less just for convenience, so that you can use tables and use their names, because that's basically what it is. It basically has this member template again, right? Okay, and this is what the table template looks like. So it takes the table for CRTP, and it takes these column specifications, and then it inherits from, in the end, a member template, which is the member template inside this column specification, which has the appropriate name, and it's the template argument is a column following this specification, the column specification and the table information, so that it knows to which table it belongs to. And this gives the member the correct type, right? And what we end up with is a table that contains, for each column, a member with the appropriate name from that member template, and the appropriate type, which is the argument of that member template. Okay? Sorry. Okay, questions about that? Yeah.
Where did the lowercase dot feature, have you described that yet? Like how you get the actual names of the member variables, like dot feature, dot lowercase name, dot lowercase feature?
Okay, so the question is where does the dot name dot feature come from?
You showed the feature was uppercase F.
Oh, right. So the question was where does the lowercase feature come from? Well, from this member template here, right? So the uppercase, that's just the name of the specification for this column. That's not used anywhere except for defining the column, and it appears in some error messages. But other than that, the important part is what's in here plus these traits. And if this looks daunting to you and you don't want to write this, then you're right. You shouldn't. You should never write this by hand because, well, it's ugly to write this, and you could make too many mistakes. And when you do that, you will do copy-paste stuff and mix it up, and you will be no better off than where you were with the string-based stuff. So typically, what the users that I know of for this library are doing is they have a code generator. So they use the table definition for the database that they are going to work with and generate this code from it. The library comes with an example script which works pretty well with MySQL. Matthijs Müllmann, who did the connector to Postgres, wrote a script which works with Postgres. And if you're using another database and none of these scripts works for you, it should be easy to adapt. OK, so we seem to have nobody here to tell about the time. So OK, half an hour. Right. OK, questions about how this works? Yeah. Sorry? As. Basically in the same way as this. So the next slide I'm going to show you is how it works in the result first. And I'm not going to show you the full code of how the result works because that doesn't fit on the slide in a reasonable way. But the individual fields are constructed in basically the same way as the column members. Individual fields have some field specification which is derived from whatever you've selected. Each field specification, again, has a such name type, including a member type. And then you instantiate the member type template with whatever field you just want to have. Right? So the type is relatively easy. Everybody knows about types. If we know that we're selecting an integral value, then OK, this field specification would basically say, OK, this is an integral value. OK, and aliases, I don't have a slide for that. But basically, what it does is, so either you already have a name, like with this feature column that already has a name, or you construct one with this macro I showed you, and you construct something with a name. And basically, what you do is you wrap your object into something into some type which contains the right name. Does that answer your question? I know that's a bit abstract, but I don't have a slide for that. Oh, OK. OK. So I don't think we should go back to that part of the talk yet. Maybe later if you have time for questions. Yeah, no problem. But if we have later time for questions, we could go back to that, but not right now. OK. But in the end, it's just using these name structs, handing those around, because handing around structs is easy, and assigning those to internal types of whatever, that's easy. And this is how names are handed around. OK. Good. And the same applies to parameters, of course, what we've seen earlier when we have name parameters. That's just the same stuff. Yeah.
So when you say result dot name and result dot feature, how do you introduce those names
Yeah. So it's very similar to this table definition. This is a variadic inheritance, I call it. So you inherit multiply from an unknown number of columns. And for the result row, it's just the same. You inherit from an unknown number of fields, and each field carries the member with the appropriate name and type. And it takes some code, but if you understand this basic principle, I think pretty much everybody in this room should be able to understand what's going on in the code. Okay, so constraints. Yeah, I've showed a lot of constraints and how this library tells you what you're doing wrong if you're doing something wrong. And yeah, first of all, I'm so looking for ConceptSlide because I think this will make my code much easier. Yes.
If this is the way you feel, well, have you considered using the Boost concept checking library until ConceptSlide becomes available? There's a one-to-one correspondence between what's in there and what ConceptSlide has.
Okay, so the question was if I was considering using Boost concepts. The Boost concept checking library. Okay, sorry. The short answer is no, I haven't considered it yet. And the reason is that until now I haven't been able to get something to compile with it for whatever reason.
So you considered it and found it to not work?
I've considered it and tried it with the compilers that I use, with examples that are directly from the library, and I found it not to work in my setup. Sorry?
No, I mean that would be a good reason for not doing it.
Yeah. So yeah, it just didn't work for me.
It's a good explanation.
Yeah. Okay. So maybe I'm doing something very terribly stupid there, but well. So for now, since we don't have ConceptSlide, and I'm obviously too stupid to use the Boost library, I'm doing something like this, doing static asserts in several places, and this would be the condensed version of what's happening when you set values in an insert. So let me just walk you through this. First of all, I assert that there's at least something which is set, because otherwise the whole statement wouldn't make sense. Then I check that everything is in fact an assignment. That's what this all is assignment thing is doing. Then we check that there are no duplicate columns, so no has duplicates on the left-hand side arguments of these assignments. Then we check that all columns are from the same table. That's reasonable. Since the table definition, or the table definition is part of the column definition, as we've seen before, you can make basically sets of tables from these assignments, everything at compile time, and then check if the size of the set is 1. So that's very simple. If you have a typeset, that is. But typesets are not that difficult either. And then we check these required and prohibited semantics that I showed you in the examples earlier. So if the set of columns that you have in the assignments does not match is not a superset of the required columns for insert, then, well, you have a problem. And same with the must not insert columns. If any of the assignments contains a column which is defined as must not insert, then okay, we have another problem. Okay, so this is the basic idea of how this works, and of course it gets more complex if you get to the point where you really want to send the statement to the database, because at that point you have to combine all the different parts, especially in a select. You have to make sure that all the columns match to the tables in the from, and that the where doesn't do anything weird. And I also transport information about whether a column can be null into the result thing. So of course, can be null is a trait of a column, but that's not the only point where something can be null. You can have outer joins, for instance, and then the tables in the outer parts of the join, their columns can be null by definition because they are in the outer part, and so every column that is in the result set, which is somehow related to an outer table, that can be null. So all this information is done at compile time, and so it doesn't always look. Is it fair to say simple? Anyway, it doesn't always look that simple, but I try to do it as cleanly as possible so that it's understandable by a casual reader, if possible. Okay. Questions about that? Okay. Now, one of the important part about this library is that it's completely vendor neutral. It doesn't know anything about any library, about any database at all. So it doesn't know MySQL, it doesn't know Oracle, it doesn't know Postgres, nothing. But of course, you have to, at some point, you have to connect to a native database in some way, and that's where these connector libraries come into play. They are the glue code between the vendor neutral SQL++11 library and the native database interface. And one of the questions that always comes up, of course, if you're operating with SQL++11 and SQL++11 is vendor neutral, then how the hell does it work if my library, if my database does something very specific, which is maybe not in the standard or is a deviation from the standard? I mean, I think pretty much every database does that. And here are some answers to how to do that. Because yeah, you can make all this special behavior of databases work in the same way as the rest does. The same compile time checking, just a little bit of work to be done by someone who does the first connector library. Most of the stuff would be typically done at serialization. So assuming that your backend uses strings to communicate with the database, then in the end, and behind the screens, unknown to the user basically, you will turn the expression into a string, right? Which is not so bad as the strings that we've seen before, but yeah, you turn it into a string and then, okay, send it over. Okay, question?
Is that where you would prepare a statement?
I'm sorry?
Is that where you would prepare a statement if you wanted to prepare statements?
Yeah, well, you missed the first part. So, yeah, there is a function for preparing statements, and that goes in a very similar way. So typically, if you have a string-based backend, what you would do is, so this is part of this glue code library, the connector library, you would create some kind of serialization context, which is specific to your library or to your database, and then call a serialize function with the statement, or in this case, the select, and the context, and then do something with the results which are written into the context. And this is what the serialize function looks like. Not doing very much complicated stuff. Basically, it just dispatches a call to a serializer template, which is instantiated with this context type, and wherever expression or sub-expression you've given it to it. And it calls a static method of that. And the reason for that is that I can do partial specialization, which we cannot do for functions per se, but we can do that for types. So we do partial specialization with something where the general case looks just like this. And it says, well, I can't serialize this because there's a specialization missing. Yeah.
Maybe I'm missing something, but if you're in C++ 14, you might want to use variable templates for that. Just saying.
Okay. Yeah.
It could be just similar, it's simplified, right?
Yeah. Okay. So the comment is that in C++ 14 I could use variable templates with lambdas, right? Yeah. Currently I'm stuck to C++ 11, and the next move I'm going to make is when concept-slide are available in Clang, I guess. Okay, but yeah, we should talk about that. I'm not sure if I know exactly how to do that.
Basically, you put the body static S or ground, blah, blah, blah. This is really just the body of a lambda.
Mm-hmm.
And
Ah. Okay, yeah, get it. Okay. Okay, so now in the SQL++11 library, there are specializations for the serializer for all components that you could have in your statements. So there is one for assignments, for instance, and for columns, and for tables, and everything that you have in that library has a specialization, partial specialization for this, and it uses a generic context and a specialization for this type T, which is then the expression part that you're looking at. And if in your library you want to disable something, then you can just make another partial specialization, which then is specific to your serializer, in this case for the SQLite serializer. And it takes a look at a join, which is an outer join, and then some whatever you want to have, so you don't care about the tables. That's why it's partial. And SQLite does not support outer join. So what you do is you make a partial specialization for your serialization context, and this way override whatever is in the library. And this way you can switch off SQL features at compile time. Okay. Now we come to a concat example, which is not exactly what you asked before, but the serializer for concat in the library itself would use the concatenation operator, which I think most SQL libraries use and which is the standard. And MySQL has decided for some reason that by default they are using a concat function. So if you're working with the MySQL database, then you would want to use the concat function. And the way you do that is, well, you write a partial specialization for the serializer and the concat, and a concatenation object, and then just serialize it in the way that you should for this database. Does that make sense? Okay. All right. Now, these were just minor adjustments to what your database might do slightly different than the standard database. But what about if you want to have something completely different, like new types in the database? These examples are by Adam Wilkowitz, and he said, okay, I have a geometry library at Boost, and databases are using geometry functions and types at an increasing rate. So what about adding these? And I'm not going to go into all details because 1 hour is far too little time to do that. But it's not so complicated, because what you have to do is, well, you have to define types that can interact with whatever kind of data types you have normally for this kind of calculation. And you would have to add some functions similar to this, to the concat function that we've seen before. Have basically a concat type that contains the information that you need to carry to the database or need to take back from the database. And then write a serializer, and more or less you're done. Okay, so This is a very brief overview of what you probably would want to do in that case. So this is from an integral, and there is a lot of boilerplate in those files, but basically you can just copy-paste this and replace everything that has information about the type and about the C++ representation of it, and yeah, just replace this with whatever type you want to have. Okay, so you have a basic integral type, which says what the C++ equivalent of it. You have some expression operators that everything that that claims to be a, then in this case, geometry expression would inherit from, so that you can have also member functions like intersects or distance or whatever. You would have some column operators, which are typically just assignment. You would have some parameter representation, so that you can use this new type in a prepared statement. And you have result fields, which are able to get this information from the database and give it to the user. So, well, we can't go into trying to implement that here, of course, but that is all you have to do to introduce a new type. And new functions are very, very similar. You just add a function, it returns a specific type or a specific template, and then you write a specification, a specialization for the serializer, and you're done. Okay. So, yeah, just skipping briefly through these. So this is what the like method looks like for a string. That is really simple. It doesn't contain anything except for a type check. This is what the like itself looks like. That is very close to what Jens asked earlier. So if I select something with a like function, then this thing already has a name. And the same would apply to concat or count or anything else. This is just for convenience. Objects that, or classes that represent parts of the statement sometimes have a name if it's likely to be useful. And at the bottom you can see that, well, it contains the operand and the pattern, so it stores just the information, and it's just one part of the expression tree that we're building here. Yeah, as I said, as a serializer, and you're done. What you also can do is, because I mean this is still limited, you're still limited to the basic way that these select and insert and everything works. What we have done now is we have added functions, we have added new types, but we haven't changed the structure of the statement. And for instance, like Oracle has this feature that I don't really know what it does, but they have hierarchical search, right? And that is something that sounds neat if you have a hierarchy in your tables somehow. That is something that you couldn't currently do with how the statement looks like. But in the end, a statement is just a veridic template, gets some information about a database in some cases. It says, okay, it's a select. And then in the initial state, it has no flags, so no distinct, whatever. It has no columns, no from, no where, and so on. And when you start to use it, you replace. So when I call from, for instance, then I call the method from, which is provided by this no from type. When I call the method from, then I'm getting a new object back, which now represents the statement, and that has a different type in the place where the no from is. So it now has a from. This from does not have the from method anymore, so you can't call it twice. You're protected from that. But it contains the data now of your from call, right? So that is how these statements work in principle. And of course, if you want to add a new feature to that, a new subclause, well, that's easy. You just have to write these kinds of pairs. So you would have to have one template that contains the initial state, where you have an additional function, or maybe several, which then return the change statement, which has then the second part, which just is there for keeping the data and for serializing the whole thing. Right, a few minutes left. All right. Now, I said when we're talking about serializer that, well, most databases use strings in their interface. And so we're going back to strings. But if there is not a string-based interface, what do we do then? Okay. In that case, there is an interpreter which looks pretty much exactly the same as the serializer. There are no specializations at all in the whole library, and you're on your own. You can now use the expression tree in any way you want with this interpreter and just reinterpret it in any way you feel reasonable. Okay, and ideas. What you could do is you could serialize, I mean, this would again be a serialization, but in a completely different way. You can serialize the code into a Python script for extracting data from HTML. So you could extract data from HTML with an SQL interface if you wanted, and if that's useful in some way. Or you could convert it into some different expression tree. That is one, skipping over that. That is an experiment that I'm working on whenever I have time for it, which is too rare. But it took less than a day to write an SQL interface to std vector. And what I can do now is I can insert code here. I can use a vector of this sample struct as a database, insert values into it, and then select from that. Right? Just select. Yeah, that doesn't really. That part is not exactly good yet. But I'm selecting from this table with this expression. I have new code which also contains order by, and so it's relatively simple to just turn around those expressions into a new expression at compile time. So this is not some runtime evaluation of the expression tree. It's a compile time evaluation of the expression tree, and it basically returns functors, and these functors do what they should do to make this feel like SQL. And it is SQL for vector in this case. All right, so there are no limits, I think. You can try to query whatever you want. There is some work that you have to do in writing a connector if the database isn't connected yet. But yeah, ODBC would be nice. There are some people who want to use SQL and NoSQL databases. I don't know why they would want to do that, but I've seen several posts of people who want to do that. Containers I've just shown, would be nice to have people working on that as well. Streams, of course. XML would be a nice example where you could benefit from this. JSON, I don't know, there are many things. Okay. Right, thanks to everybody who uses this library. It's a huge honor if people use this, because there's a lot of work that went into this, and in the last 2 or 3 months, it finally took off and people start using it, and that's pretty exciting. So everybody who uses it, contributes to it, questions about it, listens to me when I talk about it, spreads the word. Thank you very much. And of course, thank you.